Okay, so welcome everyone to the Colloquium. Today it's my great pleasure to introduce Dr. Efimov, who will speak about categorical noncommutative geometry.
Thank you. I'm happy to speak here. So it's the fifth talk here, but it's a colloquium. I'm going to give a very brief overview, basically, of maybe just the idea what is categorical noncommutative geometry. So what kind of objects that we study, what kind of problems there are people trying to solve in this field. So just a very basic idea is that so if you have some quasi-projective variety, quasi-projective variety or scheme over some base field, then you can associate this derived category. Well, there are different versions. The most basic one is the category of perfect complexes. So basically, the objects which you consider are just complexes of vector bundles, bounded complexes of vector bundles, something like n and so on. The differential square to 0, and so morphisms are obtained by, so take naive maps of complexes, and then invert quasi-isomorphisms. So this is kind of the basic categorical invariant associated to an algebraic variety or a scheme, and maybe one of the most famous results in this field, which is 97, I think. So it's theorem of Bondel and Orlov. That in many cases you can just reconstruct the algebraic variety from this derived category. So if K is algebraically closed, and if X and Y smooth projective varieties over K, and if you just assume that, let's say, canonical bundle on X is ample, or its inverse is ample, and then equivalence of derived categories, let's say, of perfect categories of perfect complexes, just implies that the varieties are isomorphic. So this is kind of reconstruction theory. And in general, it's known that derived if you consider all possible varieties with the same derived categories, then there will be this will be at most a countable set. So this is quite a powerful invariant, just even from the most naive point of view, that in many cases you can just reconstruct algebraic varieties from this variant. But maybe more importantly, just a lot of usual invariants of schemes like Rham cohomology, they can be essentially recovered from the derived in a natural way. Now the idea of noncommutative geometry is basically instead of idea of non-commutative geometry in this categorical approach. So just consider triangulated categories. Instead of algebraic varieties. And so this is kind of very naive slogan, but surprisingly, it turns out to be a really beautiful and rich theory. So, so to make it slightly more precise, I need to define the notion of a differential graded category, because kind of if you approach this in the original axiomatics by like if you consider the original approach like by due to Grothendieck and Verdier, then it's not flexible enough. So you need slightly more refined version of this category, so that there is an abstract notion of a differential graded category. Let me just give this abstract definition, and I'll explain how this works in geometric examples. So differential graded category over T is the following data. So first, as usual, we have objects. Let's say C and T. So we have objects of C. Let's say it's a set or a class. It doesn't really matter. And for two objects, X and Y in C, we have a complex of morphisms from X to Y. So it's a complex of vector spaces over K. And 3 is that we have a composition. So for X, Y, and Z, a composition. So A, Y, Z, answer A, X, Y to A, X, Z. And so the conditions are the usual ones that we have associativity. Associativity and identity morphisms. So the usual condition that we have identities and the compositions are associated. And so the basic example of this coming from algebraic geometry. I'm not breaking the board. Works. So the basic example is consider again. So X is a quasi-projective scheme of variety. Then consider this. Well, there are different versions, but consider the category C such that objects of C are just data bounded below complexes of injective quasi-coherent sheaves. So bounded below, I mean cohomologically, the cohomological grading. So it's object of the form. So we have like 0, 0, 0, and some n plus 1, on where each fi is injected. And then when we have two complexes, sorry, it's the indices would be upper indices. And when we have two complexes, we just take the usual complex of morphism between them. We can consider just the whole category like this, but to relate it with the category which I mentioned in the beginning, we can just require that F would be quite isomorphic to a perfect complex, to a complex of vector bundles, the bounded complex of vector bundles. Then C is a well-defined Dg category, so C is a refinement, can be considered as a refinement of this original triangulated category of perfect complexes. So it's also called actually enhancement. Dg enhancement, differential graded enhancement of complexes. From now on, let me just ignore this distinction between like original language of triangulated categories and this more refined language of differential graded categories. But by refinement, I mean that more precisely that homotopy category of C is equivalent to this original triangulated category. So objects are the same, and morphisms are obtained by taking the zeros cohomology of the complex. So more generally, if you have a Dg category A, you can always produce the usual category, this homotopy category. Its objects are just the same. And maps are obtained by taking zeros cohomology of the complex of morphisms. Okay, so this is a little bit of at least one necessary abstract definition of a Dg category. Now, the slogan, kind of refined version of this slogan is that non-commutative scheme is so non-commutative schemes are just the same as small differential graded categories. Well, up to equivalence. Now, to make it kind of more interesting, so instead of just a slogan, let me formulate at least the analogs. I mean, to start, let me formulate the analog of basic notions like smoothness and properness. The basic definitions due to Kontsevich are that if so let A be a Dg category of the base field, then first that A is proper or compact if the morphisms in this Dg category are like perfect complexes of vector spaces. since we are working over a field, this just means that the total cohomology, total cohomology of this complex is required to be finite dimensional. And there's also a notion of smoothness. A is smooth if well, you can make sense of the diagonal bimodal diagonal object if the diagonal object is perfect over A tensor A opposite. So basically the usual notions can be translated into this abstract language, and the basic comparison result, just compatibility result, compatibility with the usual algebraic geometric notions. So this is due to Lunds and Orlov. Is that if X, let's just say quasi-projective over a field, then X is smooth if and only if the categorical perfect complexes is smooth. And second is the same for properness. X is proper if and only if the categorical perfect complexes is proper. Yeah, these are not difficult to prove if you, if you just have a little bit of experience with working with such categories. So basically, this smoothness, if you just translate the categorical condition, you see that it's equivalent to the condition that the diagonal, the structure shift of the diagonal of X in the product has a finite resolution by vector bundles, and which is the same as usual smoothness. And for properness, like it's roughly speaking, it's just finite dimensionality of cohomology of coherent sheaves. And yeah, and in the non-trivial direction, you need to also use the validative criterion of properness, but it's basically quite easy to prove this compatibility. Yeah, so you have this general analogs, this non-commutative analogs of the usual smoothness and properness. Now we can actually push this further, and in particular, we can talk about smooth compactifications of smooth schemes just in this non-commutative context, just purely in terms of categories. And so first recall that there is a basic construction called the quotient. So if A and B are, I didn't mention this, but informally, let's call, there's a notion of triangulated DG category, which roughly means that its homotopy category is triangulated in the usual sense. So if you have triangulated DG categories A and B, and A is the full subcategory of B, then B mod A is the quotient category. I will not define what it means in detail, but in particular, the most important property is that formation of this quotient is kind of compatible with the usual quotients for triangulated categories. So there is a universal way to kill the objects of A. So the basic geometric intuition for this notion is that if you have some closed subset y in X, so if we're talking about algebraic varieties, so if y in X is a closed subscheme, then we can take perfect complexes on X and mod out by perfect complexes on Y, and we will obtain the perfect complexes on the complement on X minus Y. So intuitively speaking, like the categorical quotients are just kind of general version, this non-commutative version of taking the complement to a closed subset. And now we can these are quite abstract definitions, but I will give some particular examples of situations. So one can define the general notion of a smooth compactification. So if A is smooth, then smooth compactification A is a functor from some C to A, where C is smooth and proper, and C induces an equivalence of the quotient of C by some subcategory and A. Well, up to direct summons, but it's not so important. Economic completion, yeah. But roughly speaking, A is obtained by taking quotient of C by some subcategory. So the basic geometric example of this is if you have a usual smooth compactification, then the pullback functor from perfect complexes on the compactification to perfect complexes on X is this categorical smooth compactification. So to distinguish, let's call this categorical smooth compactification. So this is categorical smooth compactification. So this notion is actually quite important in this context of categorical smooth compactification, and in particular, one can ask the very naive question: is it true that any smooth category, let's say of finite type, over a field K, let's say characteristic 0, is it true that any such category has a smooth compactification? So, like, is it true that Hironaka's theorem holds in this non-commutative setup? And surprisingly, the answer is no, for some non-trivial reasons. But still, for for sufficiently many smooth categories, essentially for almost all of them up to retracts, such a computation can be constructed. And so let me give some interesting examples of this coming from algebraic geometry. So I mentioned the compatibility of this notions of smoothness and properness with the usual notions for schemes when we take perfect mixes. But there is a kind of surprising result due to variety looms that if X is, again, let's just consider quasi-projective schemes over K, and K is perfect field, then derived category of coherent sheaves in X is always smooth. So there are no assumptions on the singularities on X. So, and X is also not required to be proper. It can be just any quasi-projective scheme with arbitrary singularities. Then derived category of coherent sheaves is always smooth, and this basically, essentially, it reduces to existence of dualizing complex. So it's not so difficult to prove, but it's just it was unexpected that when you take coherent sheaves, any scheme becomes smooth in this sense if you shape this version of the derived category. And then I have this general result, which is quite difficult, which is refinement of this theorem. So let X over K quasi-projective, and assume that K is of characteristic 0. Then there exists a smooth compactification categorical smooth compactification from C to dB Koch of X, and in fact, C can be chosen in such a way that C is equivalent to derived category of some Y, where Y is smooth projective. This is one example of situation when the construction of a smooth computation is really difficult, and this uses Hironaka's theorem. Plus the construction of Kuznetsov and Lund's categorical resolution of singularities. And remark same holds for derived categories of D modules as well. I mean, you have well-defined derived categories of coherent D modules also for single schemes, and in fact, it can be proved that there exists a smooth categorical computation for these categories. Yeah. Now, so yeah, we had this general question about existence, and now let me mention kind of a positive result in this direction, which has many applications. Theorem is that for sufficiently large class of smooth categories of finite type, you can construct smooth complications, and let me formulate it as follows. So consider a DG algebra A over K. So DG algebra, you can think about it. I mean, it's just the same as DG category with one object. So basically, we have a gradient algebra with a differential satisfying the super Leibniz rule. But consider DG algebra was a very special form. So such that A and the gradient algebra is just free, and it is generated by some collection of homogeneous elements. And the differential of each of these elements is contained in the subalgebra generated by the previous element. Then there exists a smooth compactification C of the category of perfect modules. And moreover, C is actually, we can do it in such a way that C is generated by, for example, yeah, by some, let's say, by exceptional collection of some lengths where L is at most 2 to the n, 2 to the number of generators. And exceptional collection just means that endomorphism of each of these objects is just the base field, and there are no morphisms from right to the left. From EI to EG vanishes for I greater than G. Yeah. So remark this. So this construction in fact works over any base ring. So K can be any base ring, and so if you're familiar with spectra, it can be even a sphere spectrum, for example.
So is it clear that there is no kind of these like effect sizes?
In this case, it is quite easy to check. Yes, yes. But also, like if you're able to construct a smooth computation, then the category has to be smooth. But here it can be shown directly just by resolving the diagonal. Yeah, you can just write down the resolution. Yeah, and so now, okay, let me give a simple example of how this works.
That's a question about the definitions.
Yeah.
First, that X is smooth even only if perfect complex is on X.
Yes.
But then for the other theorem, you say that dBx, the coherent derived category is always.
Yeah, but I mean, if the scheme was singular, then dB coh is bigger than perfect category.
Yeah, but you never told us what it means to be smooth for a triangular category. Is that right?
No, I did. Well, okay. Maybe I didn't give you like the complete definition, but I said that the diagonal bimodule must be perfect. So if you just assume that this category is like perfect modules over some algebra, then that just means that this algebra as a bimodule over itself is perfect. So this is
maybe also you could just take the objective resolution definition, but now impose it because that's something with greater cohomologies.
Yeah.
And that's the DB replacement and probably
yeah. Yes. Yeah. yeah, so yeah, yeah, so you have this abstract definition, and in the case of Efimov, yeah, you can just apply this definition to the particular DG category formed by injective resolutions of coherent sheaves. Yeah, so okay, so let me give a simple example of smoothness. Where it is easy to understand how this works. Example, to consider this DG algebra, which is in fact just lives in degree 0 and is just the usual free algebra on a finite number of generators. So so every generator is in degree 0, and so yeah, the differential of all of them is also 0. Then we can construct a computation of the following form. So then we have, let's say, short exact sequence of categories. So we take our category of perfect models over this algebra, and we have a natural function from representations of a quiver with 2 vertices and n+1 arrows between them, call them E0, etc., En. And we take representations in perfect K modules. So if K is a field, then this is just basically a derived category of fine dimensional representations of this field. That's quite a classical object. This functor is actually obtained by modding out by the subcategory generated. Let me write this informally, by cone of E0 of one of these n+1 edges. So basically, this operation is we just inverting. We're just inverting one of the arrows, and at least informally, it's easy to understand what happens. So you had this oriented graph with 2 vertices and n+1 edges from the first vertex to the second vertex, and you just declare that one of the arrows is kind of invertible, and then you can just instead of 2 vertices, you can just consider one vertex, and you have just n loops, which are still remaining here. So that's at least intuitively, it's very easy to understand, and it's also not difficult to make this formal. So basically, you invert one of the edges, and you get free algebra on n generators. So that's kind of a very simple example, and so if n equals 1, then we get just the usual quantification of a fine line by P1. Just so we have just this algebra generated by x1. We have the usual quantification by the projected line. So this is but if n is greater than 1, this is just a kind of non-commutative object, but still quite easy to understand. But if you consider this algebras of this form where differentials are non-trivial, then in this way you get essentially all finely represented smooth categories up to retracts. So this is kind of a useful result, because it tells you that almost all finely represented categories can be compactified. I will probably not mention this application, but it's useful in understanding localizing invariants of categories, in particular the universal localizing invariants. Okay, now let me also mention the negative results. Like examples of cases which cannot be complexified. So like Hironaka's theorem doesn't work in this kind of non-commutative context. And for this, let me recall first the notion of cohomology. So if you have an algebra, or a DG algebra, then we have this cohomology. We consider it as a complex, but you can also consider it just on the level of graded vector spaces. So cohomology of A is given by taking just derived tensor product of A with itself as a bimodule. So it's tensor product over A tensor realities. So basically, this is non-commutative analog of differential forms. So if if A is commutative, so this theorem of Hochschild-Rothenberg, A is commutative and it is smooth. So let's say its spectrum is smooth. Then this HHN of A is just the differential forms. So cohomology are identified with differential forms, and then it was an amazing discovery by Kohn and independently by Fagan and Sigon, that there is actually an analog of the Rham differential. Let's say an analog of the Rham differential. This can be written like in terms of complexes. You can write this that there is a so we have this Hochschild complex which has the differential which commutes this Hochschild homology, but there is also this Kohn differential. And like in the degree of B, let's say cohomological degree of B is 1. So B is like the usual differential, and this B capital is a degree -1, and then they supercommute with each other. So in particular, this Kohn differential induces a differential on the host homology of spaces, and for this, let's for simplicity assume that characteristics is 0. Then so this Kohn differential on the host homology groups is just the same as the Rham differential. So this is the Rham differential under this identification with differential forms. Okay, but now this differential, so the definition, it kind of makes sense for all DG algebras and in fact for all DG categories. And then there is it turns out that like non-trivial results like Hochschild-Rham generation degeneration of the hot to the Rham spectral sequence, they hold in this non-commutative setup. So so if X is smooth and well, let's just say smooth projective over K, and K is characteristic 0, then the classical Hodge theory over complex numbers implies that this spectral sequence, which starts with cohomology of sheaves of differential forms, just the Riske cohomology, to the Rham cohomology, that it degenerates. All the differentials in the spectral sequence vanish. And in fact, well, up to without specifying the gradings, the theorem of Cauchy-Rosenberg in the non-affine situation, so for general schemes, it identifies Cauchy homology with the cohomology of differential forms. Let's not specify the gradings. And there is a version of variant of Cauchy homology, kind of the analog of the Rham cohomology, which is kind of two periodic. So this two periodic version, so the two periodic invariant is identified with the Rham cohomology. Again, without specifying the gradings, but basically it's two periodization. So let's just say that these are like Laurent power series in U, where U has degree 2. And theorem of Kalezin, and yeah, mentioned that there's another proof by Achille Mathieu, that if A is smooth and proper DG category, then the spectral sequence, which starts with Cauchy homology, like two periodic version, and converges to periodic cyclic homology, that it always degenerates. Yeah, and yeah, so this is like fundamental result, just kind of saying that this degeneration can be understood purely categorically, roughly speaking, by generalizing the Delim-Illuzy method of proving the classical degeneration by reducting mod P. Yeah, but now I mentioned this question about the existence of smooth computation, and it turns out that this theorem actually gives a linear algebraic abstraction to the existence. Let me explain this.
Sorry, just to make sure, without any characteristic.
Sorry?
The characteristic.
Yeah, sorry, yeah, here, yeah, the same assumption, yeah, yeah, again, the field is 0. Then, so observe this portrait to cyclic degeneration can be reformulated like there is this version of cyclic cyclic homology, like negative cyclic homology, for example, and so it can be just formulated in terms that in terms of the boundary map. That the boundary, so that means that the boundary map to the negative cyclic homology, well, restricted by -1, is the zero map. So this means this means that this negative cyclic homology is like taking power series this variable u. So basically taking this shifted copies, direct sum or direct product of shifted copies of quotient homology, where u is of degree 2 homological. And so now you can observe that if A is smooth and has a smooth computation, then this has a linear algebraic consequence. So you can take this quotient homology of the A tensor opposite, so this has an element degree 0, which is just term character of the diagonal, and you can take the boundary map. So you can take like identity tensor delta, go to HH of A, tensor HC minus the opposite, and then this element goes to 0. So it's actually easy to deduce this from existence of a smooth computation. And yeah, and also like another corollary. Okay, I mentioned it on another blackboard. Another corollary that if A is proper and if you assume the dual condition and there exists a full embedding of A into C, where C is smooth and proper. Yeah, again, for both of these corollaries, I assume that characteristic of the base field is 0. Then this composition. So if we take HH of A, tensor HC of A, so this is just another kind of dual variant of HC minus. So that there is a boundary map. Let's also call it delta, goes to HH, tensor HH the opposite. Then we have an initial pairing to K, and then the corollary is that this composition is actually 0. So these are like consequences, like either of existence of smooth computation or of existence of embedding. And so there was a conjecture of Kontsevich who tried to understand the Rham generation kind of like algebraically, but like kind of in an elementary algebraic way in terms of certain identities, so that he wanted to have algebraic proof of post Rham generation, but without any need to reduce to HSE, so without any complicated methods. So the conjecture was that let's just say that conclusions of this corollaries, let's call it corollary 1 and corollary 2. Hold or any smooth respectively proper DG categories over K. Again, K is a field of characteristic 0. And then, so remark, so this conjecture was believed to be true because, so this conjecture holds for all categories, DG categories coming from algebraic geometry. From algebraic geometry, and in fact for all categories coming from symplectic geometry. So if you consider Foucault categories in symplectic manifolds. But unfortunately, so I proved that conjecture is wrong. So it's false. For so it's like both for proper and for smooth categories. So if you consider categories which don't necessarily come from algebraic or symplectic geometry, then unfortunately this no longer holds. So in particular, you cannot really hope for a purely algebraic kind of elementary algebraic proof of post-Rham generation. The categorical setup. Yeah. So and okay, remark. So these counterexamples are a little complicated, but so the counterexample for proper categories is given by a certain by a 10-dimensional anything C algebra, such that the super trace of like M3 iteration M3 on the second argument is non-zero. So this so basically this post-Rham generation, if you translate it in terms of this higher operations, it translates into vanishing of this super traces, for example, of this one. But you can construct 10-dimensional infinity algebra for which this vanishing doesn't hold. And okay, I think I'm essentially almost out of time, so I think it's a good point to stop.
Are there any questions?
In your theory, what you stated about smooth compactification, is there any relation between the y that you get to the original x?
Well, there is a relation. Okay, let me, if I formulate it in a slightly different form, okay, let me write it here. So if I want to construct quantification of x but not necessarily such that the category is not necessarily the derived category of something, but if I wanted just to be a semi-orthogonal gluing of a few categories of this form, let's say some y1, that are yn, then this, so assuming this x is proper, which you can always assume because you can first compactify it. These yi's are either smooth center, like let's say one of the smooth centers in the blow-up process, which gives you the resolution, or the resolution itself. Yeah, and more precisely, I mean you resolve singularities of the reduced part of x, reduced of, and if you do it by a sequence of blow-up of smooth centers, then basically the varieties which appear here are either the centers or the resolution itself. Maybe each of them can participate finite number of times. Yeah, so it's a difficult result, but it eventually reduces to Kernakis theory.
They are precise definition of which categories coming from algebraic geometry.
What I mean, let me say what I mean more precisely. Like for smooth categories, I'm basically considering this dB x, where x, let's say, separated to finite, because we know that all of them are. Yeah. And for proper, I'm considering, let's say, perfect complexes on some, again, some separated finite type scheme supported at some closed subset y, such that y is proper. So for all of these categories, the conservation conjecture holds. So for this reason, like the most difficult of disproving it, the difficulty of disproving this conjecture was mostly psychological, because I believed that it should be true for this reason, but in the end it turned out that it just holds.
So it was believed that, so just as every smooth variety is smooth compactification, it was believed that every smooth category.
Yeah, smooth, let's say smooth of finite type. Yeah, that it has smooth compactification. Yeah, so it was just kind of the basic assumption, which people just believed it just from. Yeah, it was just the basic intuition of the geometry that this should be true, but and for that reason it was difficult for me to disprove it, just because I did not try construct counterexample, but then it turned out to be just wrong.